Hello everyone, today the work I'm gonna present is a collaboration project between Alibaba Group and Indiana University Bloomington. The title is Adversarial Multi-Scale Anomaly Detection on High-Dimensional and Time-Involving Categorical Data. The reason why we work on anomaly detection is because of its increasing importance in real-world scenarios. It can provide a wide range of applications, from capturing rare events or unusual observations to protecting a complex system against failures or attacks. It can benefit model training on downstream tasks as well, such as cybersecurity, online recommendation, and advertising. Moreover, it requires to be applied in more complex scenarios. If we take a look at the figure on the right, we can see that it is a data pipeline of user logs. The user logs are time-evolving data and comes in sequence. Each piece of the user log comes with a set of different features, such as clicked item IDs, favorite brand IDs, or purchase category IDs. And within each feature, the format is a list of categorical data, which means if we encode the user logs as one hot encoding, each piece of the user log will be super long and sparse. Moreover, the reason to cause the anomaly comes from various reasons, such as system temporary breakdown. In that way, during that time period, all the data comes through are most likely to be anomaly data during that time period. Therefore, if we can identify the anomaly blocks and the anomaly instances at the same time, we can better understand the user log data as well as detect anomalies at multi-scales. Therefore, in this paper, we aim to design an unsupervised framework for two-level anomaly detection on high-dimensional data. The two levels we consider here are instance and block level. The assumption of our work is that normal data should have concordant patterns in their representations, meaning that their representation either be similar or can have hidden connections with each other, while for the anomaly data, they should be quite different from the normal data. Therefore, we design an adversarial autoencoder to train on normal data. After it's converged, the reconstruction error on the normal data should be small because it can better identify the normal data distribution patterns, while for the anomaly data, it's not able to identify the anomaly data's patterns, and the data reconstruction error can therefore be used as the indicator to detect the anomalies. It can be taken as a cutoff threshold. If the reconstruction error of instance or blocks are over a threshold, they will be taken as an anomaly. Otherwise, they will be regarded as normal data. In our approach, there are several challenges here. The first one is data changes across time, meaning that the data is time-involving data. Previous normal data probably will not be normal in the later time periods. The second one is labeling is expensive. That's the reason why we should apply an unsupervised framework. The third one is the data format is complex. As the figure mentioned in previous slides, the data is high-dimensional and sparse categorical data. The last challenge is that we need to detect anomalies at multi-scale, meaning that we should detect at both instance and block level. The figure shown in the right shows the overall pipeline in our project to detect both instance and block level anomalies for a user log system. We can see that the input of the model is in a hierarchical structure, from a feature to attribute to instance and to block level. And the feature refers to the product IDs, and the attribute is the real features, refers to the such as the click item IDs. And the instance are the piece of user logs, and the blocks are constructed by a set of consecutive instances. And in the beginning, our mission is to learn the multi-scale representations for all these four levels. and the feature levels are initialized randomly and learned using backpropagation, and the attribute representation is learned by its feature embeddings plus a self-attention gate. And then after we get the attribute representation, first part we use a self-attention to get a VS as a part of the instance representation, and the second part we use our defined relative representation gate to learn a second part of the instance representation, VR, and in the end we concatenate VS and VR together to as the final representation for instance. And as a block is constructed by a set of instances, we use the Rn structure and the set of instances as the input. The last hidden state of the Rn structure will be used as the block representation. The relative representation gate is used to construct the VR as the second part of the instance embedding. It considers both current attribute embeddings plus previous block embeddings. In this way, we involve the previous time information into our current time model. And after we get those representations done, we come to the adversarial learning part. The instance generator is a one-layer autoencoder. We involve a random noise to make the whole model more robust. And after that, we get a mirrored instance embedding from the autoencoder. And for the mirrored block embedding, we use exactly the same way as how we generated the real block embedding. We use the mirrored instance embedding as the input in a Rn structure and the last hidden state as a mirrored block embedding. In the mirrored block embedding generation part, we don't optimize all the parameters, and we just freeze them and don't optimize them. And for the discriminator part, it's just a binary classification on both instance and block level, and we want to identify which one is the real block or instance embedding and which one is the mirrored instance and block embedding. In the training process, we only use normal data as the input, but for the inference process, the testing data is mixed with normal data and anomaly data. We use the combined error from both generator and indicator as the final score to indicate whether the instance or block is anomaly or a normal. Here is the dataset and the baseline we use in this paper. The dataset we consider three different ones from both synthetic view or public view or industrial view. The industrial dataset is constructed by the real dataset from the user log system, and we consider 7 different baseline approaches, including the GAN-based or SVM-based or autoencoder-based. And the result shows here is that our model significantly outperforms the rest of the 7 models here, both in instance level anomaly detection and block level anomaly detection. Moreover, we make an ablation study to check whether each component of our model is useful or not. If we remove the noise from the instance generator, we can see that the performance is decreased a little bit. But if we remove the relative representation module in the model for the instance embedding generation, we can see that the decrease will be huge. And block loss is about a part we used in the inference part. For the anomaly inference for blocks, if we remove the block loss, you can see that the decrease is also a lot, meaning that the block level generator and the discriminator is useful for block anomaly identification. Some other findings from the previous tables are summarized here. First, the GAN-based baseline models performs best among all the rest baselines. Second, our model displays larger advantages for block level detection. Clearly, the block level anomaly detection gets more benefit from our unified multi-scale approach. Third, adding noise clearly improves the generation performance. And fourth, the relative representation of instance enriches the information extracted at high level. The final finding is that the block loss adds detection of the collective patterns to our model, which is of great importance for detecting block-level anomaly. We'll also summarize our future work here. The first one we're gonna do is online incremental learning. We aim to deal with real streaming data. The second thing we aim to do is for large-scale distributed data process. And the final thing we will do in the future is to do anomaly detection on more complex data. For example, we aim to do only our daily level anomaly detection. Thanks for the listening. If you have any questions, please send me an email to my university account. Thanks.